The premise of this presentation is that during the inflation period, the intense energy and stress on space allowed the creation of mass but prevented the creation of antimass or antimatter. As always, this slide allows the reader the option to bypass what is known or believed. Again, I do not recommend this, but if pressed for time or are only mildly curious, you may skip sections or go to the last slide, summary. Scientists have traced the origin of the universe down to a fraction of a second. According to this narrative, the creation of basic particles and antiparticles resulted directly from the available energy. These particle antiparticle annihilated each other, recreating the original energy. But somehow, a surplus of electrons and quarks was created and survived. The slight excess of quarks combined to form baryons, protons, and neutrons, creating what's called the baryon asymmetry, which led to a universe composed of matter with little to no antimatter. Within the first few minutes, protons and neutrons combined to form the nuclei of deuterium, helium, and trace amount of lithium. This is called nucleogenesis, and it ended about 20 minutes later after the Big Bang. There are a few problems with this timeline, since what time is, when, and how time originated is indeterminate. And apart from what created the Big Bang, what accelerated universal inflation and why this acceleration ended, that's undefined. To me, the most describing concept is the mechanism for creating a surplus of electrons and quarks in a universe that's symmetrical. This presentation focuses on this problem. I realize the presentation overlooks a major problem, namely that energy existed or it was formed during the Big Bang. The problem here is that in a prior video, I had defined energy as a disturbance in space, a disturbance of space, which implies the existence of space during the Big Bang, no singularity. As for energy, how this disturbance came into existence, I can't explain. The best I can do is assume the Big Bang is analogous to the creation of a black hole in our universe, and the energy was there already. But that just shifts the problem to a parent universe, namely, how did the parent universe came into existence? The problem remains. And here's where I diverge from scientific dogma. At the basis of all phenomena in the universe, I see two factors. Number one, space has physical properties, namely, it has a fabric, and this fabric has a density. This density is higher inside masses, and as we move away from masses, it drops off at a rate of 1 over r squared. Regardless of universal expansion, this density must not change. And the second one is that universal expansion acts on space and matter, and we have names for these effects. We call it gravity if we're talking about space around masses. If we're talking about moving masses, we call it inertia. When talking about disturbances in space and matter, we call it energy. When these disturbances are transferred from one object to another, we call it forces. When this disturbance moves through a large number of free atoms and molecules, we call it entropy, etc. This presentation deals with the period between the Big Bang and the end of the inflation era. I propose that during this period, time did not exist. I will be using the terms before and after, even though without time, before and after are contradiction in terms. But language creates this necessity. So even though I'm creating a timeline, what happened before and what happened later, in reality, everything happened in a moment. At the Big Bang moment, the fabric of space was hyperdense. Energy, like a coiled spring, was stationary, and matter, mass, didn't exist. Defining what an hyperdense space fabric looks like is best left to the imagination, but it creates an image of a universe that was concentrated to an extremely without actually becoming a singularity. And this concentrated space fabric also puts some restrictions on energy, namely, how can energy be concentrated, or what kind of energy corresponds with compressed space? We'll have to look at this. Let's talk about energy for a moment. Energy can be stationary, and I don't mean stationary like potential energy. I mean stationary as energy locked inside the black hole, or the way energy stored inside an electron. This is contrary to the second law of thermodynamics, that energy cannot be contained, it must move. After the Big Bang, this stationary energy suddenly expanded in what's called the inflation era, carrying space along with it while decreasing space's density. This expansion was in the form of an instantaneous acceleration, since time didn't exist yet, but again, language requires a Big Bang to start and acceleration afterwards. It would be more appropriate to say that the universe began at the end of the inflation period. This inflation period ended when energy was frozen into mass, thereby removing energy from the system, which turned universal acceleration to a constant velocity. Apart from mass, time also appeared, as I explained in a previous video. This energy was electromagnetic energy, which we define as oscillations in the electromagnetic field, and we commonly call it light. Years ago, these oscillations were visualized as transverse waves, and we still teach this analogy of light traveling as transverse waves. In modern physics, electromagnetic energy can also come in discrete packets we call photons. Which visualization we use depends on the measurements being made. Interference shows light as a wave, while the photoelectric effect shows light as a particle. More on this later. So light can be described as traveling electromagnetic fields, transverse waves, or particle called photons. And we come to accept this dichotomy as a particle wave duality of light. Classically, there are two main types of waves: transverse, longitudinal. And I understand that light is not a classical type of wave, but follow me anyway. The main difference between the two types of wave is that longitudinal waves can travel through liquid, gases, and plasma, but transverse waves can't. On the other side, transverse waves can be polarized, but longitudinal waves cannot. And polarization refers to the plane of vibration of a wave. Because of polarization and the concept of electric and magnetic fields, light wave can best be described as transverse waves. Transverse waves are defined as shear waves. They can travel through a solid, but only when there's a boundary like a slinky or hammering a long steel rod perpendicular to the length of the rod. Either way, without an interface between two media, transverse wave can't propagate. Therefore, propagation of these waves inside a fluid is impossible. So light is an electromagnetic wave composed of electric and magnetic fields. But it behaves like a transverse wave. It transfers energy and it can be polarized. Now here's the problem. In space, or the fluid of plasma that existed during the quark gluon plasma after the Big Bang, transverse waves should have been impossible. But light did exist back then. And if it was moving, it must have been moving as a longitudinal wave, not a transverse wave. To best explain some contradictory observation of wave property of light, such as the photoelectric effect and to a lesser extent the Compton scattering experiment and the ultraviolet catastrophe, light was described as having particle-like properties. But what if light behaves as a transverse wave or a longitudinal wave depending on the experiment being performed? What if light behaves as transverse wave when the instrument used is much larger than light's wavelength? such as the size of the slits in the Young's interference experiment, but when the instrument is smaller, light behaves as a longitudinal wave, such as light ejecting electrons in a metal, what's called the photoelectric effect. I realized Maxwell's equation cannot be solved for a longitudinal wave, but photons do not have electric and magnetic field. Only when you have many photons, the familiar oscillating electric and magnetic field of light emerges. And of course, in free space, you can't tell what kind of wave light is. Now, let's consider light to be wave-like. And for the time being, let's consider it to be a longitudinal wave, although the same logic would apply to a transverse wave. We know that waves can pass through each other, but when they overlap, constructive and destructive interference occur. During constructive interference, transverse waves, the amplitude increases, but in longitudinal wave, the density of the particles in the compression region of the wave increases. Meanwhile, the density of particles in the rarefaction region of the wave decreases. Afterwards, the two waves continue on their path regardless of the type of waves. The interference effect also occurs with transverse wave. But in transverse waves, the medium can expand into the less dense medium, like surface water waves in air, meaning the density of all parts of the wave is the same. So let's assume that the fabric of space has some density, and electromagnetic energy can behave as longitudinal waves. When two waves meet constructively, compression over compression, the density of space at that point increases, and when the two rarefactions overlap, the density of space at that point decreases. In the case of electromagnetic energy, the compressed fabric of space can create a particle with mass, and that particle can move away from its original point, away from the wave. In the wave, the compression is surrounded by two rarefactions. Removing the compression brings the low density rarefactions part of the wave together, which may create an anti-mass particle. Let's look at the wave below. It's a transverse wave. If we were to remove the circled crest particle, the wave would have two troughs next to each other, and that would create antimass, an antiparticle. That's what would happen in space today. Although the antiparticle has less space particles, it must have the same mass. As an analogy, if energy is added to a point spot in water, underwater, water would evaporate and create a bubble. If the bubble is allowed to rise from below and collides with some object, it will move the object equally as if it was a solid object moving upwards. Of course, the deformation of the bubble would minimize the impact. The same would have happened at the end of the inflation era. Back then, the fabric of space was far denser and energetic. The high energy and density would create a great deal of electrons and quarks, but the high density of the fabric of space would smooth out the energy wave before the antimass could be formed. In other words, the mass particle would move away from the energy waves, would reform before the antimass or antimatter could be created. Meanwhile, the massive removal of energy caused by energy being concentrated into mass ended the acceleration of the inflation era. During this stage, the universe was expanding at the speed of light, and this expansion could still rip space apart. This didn't happen because the remaining energy started being condensed into space-time to plug any rip. With nothing to slow it down or accelerate it, the universe began its expansion at the speed of light. As for mass, in a previous video I defined mass as concentrated space pixels, with energy being the concentrating factor. In the case of matter, a specific amount of space pixels creates particles with a permanent mass. But if a lesser or greater amount of space pixels or energy is involved, that creates unstable particles, particles with a half life. Light itself doesn't have mass, but it has momentum, which is a variable amount of space pixel being carried along by universal expansion. When light is absorbed by matter, matter moves, forces and momentum are transferred, and the space pixels are returned to the fabric of space. So, in summary, space may have a fabric with physical properties such as density. Rather than considering light to be a particle, light may appear as a transverse or longitudinal wave depending on the measurement being performed. With sufficient energy, mass and antimass could result from constructive interferences. In the early universe, the high density and high energy created mass, but the intense stress on space smoothed out the waves before antimass or antimatter could form.